Hello everyone, this is Dr. Bobby Basu from Heritage Business School, a faculty of Operations Research, Operations Management and Project Management. In today's class, I am going to discuss on Simplex technique of solving a linear programming problem. As you know, a linear programming problem can be solved by two methods. One is called graphical method and the second is simplex method. But the problem with the graphical method is that it can be applied to only those problems having two variables. If the number of variables is more than two, in that case, we have to apply simplex technique only. Okay? So in today's class, we are going to see how the simplex technique is applied for solving a linear programming problem. So let's proceed. We have taken a problem which contain two variables. We are going to solve it by graphical method, and then we will be applying the simplex technique to solve the same problem. So here is the graph what we have plotted for this problem, and then we find the z value at the different corner points of the feasible region OABC, and finally we find that my maximum value of z occurs at point B, and hence the solution is x1 equals to 2, x2 equals to 1, and the maximum value of z is 8. So my feasible region as per the graphical method is OABC. Now when we apply simplex technique, we will see that my first iteration or my first table is formed at origin O. And with each iteration, we are actually moving from, in fact, we are jumping from one corner point to other, right? So that we are going to see in today's class. So let's proceed. Now, the first question that comes to our mind is when simplex method is applicable. Simplex method is applicable for all LPPs having all its constraints of the type less than equal to, with the right hand side being positive. This is very important point to be considered. First, we have to make the right hand side of all the constraint positive. If the right hand side of any constraint is negative, we have to multiply both sides of the inequation or the constraint by -1 in order to make the right hand side positive. When we multiply by -1 on both sides, the nature of the constraint gets reversed. That means if it is less than equal to type of constraint, it becomes greater than equal to. If it is greater than equal to type of constraint, it becomes less than equal to. So after making the right hand side constraint positive, we have to look at the nature of the constraint. If all the constraints are of the type less than equal to, with the right hand side being positive, then only we can apply simplex. Otherwise, we won't be able to apply simplex, and we have to apply some other technique which is called B-game method or two-phase method. Okay, so we have taken this problem. In the given problem, as you can see, we have got two constraints: 2x1 plus x2 less than equal to 5 and x1 plus x2 less than equal to 3. So both the constraints, we can see that they are of the type less than equal to, with the right hand side positive, and hence we will be able to apply simplex technique. Okay. Now what is the first step in applying the simplex technique? The first step is to convert the given problem into standard form by adding slack variables. So what we have to do is we have to convert the inequations into equations. We have to convert the constraint which are in the inequation forms into constraints which are of the equations form by adding slack variables. So we get this. The first constraint, we have added one slack variable S1, and in the second constraint, we have added another slack variable S2. Now the contribution of the slack variable towards the objective function z is always 0, because the slack variables denote the unutilized resources. Those unutilized resources will never fetch us any profit, and hence its contribution to the objective function is 0. So we have converted the given form into the standard form. Okay, and accordingly we have to change our non-negativity constraint. So now x1, x2, that is our decision variables, and the slack variables s1, s2 all are greater than equal to 0. Okay, so next, after we have converted the given problem into standard form, we have to get the initial table. We have to get the initial table. Now, as you can see, how many variables are there in all? 4, right? So there are 4 variables x1, x2, s1, s2. But only we have got 2 constraints, right? So with the help of 2 constraints or 2 equations, I will not be able to get the values for all the 4 variables. So in that case, what I do is I will assume 2 variables out of 4 variables to be 0. Now the variables which we assume to be 0 are called non-basic variables. Okay, so in my first iteration, that is in my first table of the simplex, it always starts at origin, where x1 and x2, that is my decision variables, are 0. So if x1 and x2 are 0, that means s1 equals to 5 and s2 equals to 3. As I told you, the variables which we assume to be 0 are called non-basic variables. So s1 and s2 are my basic variables, and s1 and s2 are my non-basic variables. S1 and S2 are basic, and x1 and x2 are non-basic variables. So with that, we will form the first table or the first iteration. Now, every time we make the table, the structure or the format of the table remains the same. So this is the format that is to be maintained when we make any table of simplex. So first column denotes CB, that means coefficient of the basic variable. Okay, coefficient of the basic variable in the objective function. Second column stands for basic variables. So in this first case, the first table, my basic variables, as I mentioned, are S1 and S2. So what is the coefficient of the basic variables S1 and S2 in the objective function? Yes, it's 0 and 0. So CB will be 0 and 0 for the basic variables S1 and S2. Next column refers to solution value. Solution value or solution column, it refers to the right hand side of my constraints. Okay, and then comes my decision variables, x1, x2 columns, and finally my slack variable columns S1 and S2. Last column denotes minimum ratio, which we will be explaining as we move forward. Just above the solution column or the solution value, we put Cj. Now Cj denotes what? Cj denotes the coefficient of any variable j in the objective function. So as you can see, the coefficient of x1 in the objective function is 3. Coefficient of x2 in the objective function is 2. Coefficient of s1 in the objective function is 0. And coefficient of s2 in the objective function is 0. So we have put 3, 2, 0, 0. Right? Now we have got 2 constraints. So accordingly we will have 2 rows. This is my first row. S1 is appearing in my first constraint, right? So S1 and S2 are my basic variables. S1 is appearing in my first constraint, so I have written here S1. S1's coefficient in the objective function is 0, so I have written here 0. In the first constraint, the right hand side is 5, so under solution value we have written 5. And then we have written the coefficients of x1, x2, s1 and s2 in the first constraint. So that is 2, 1, 1, 0, because s2 is not appearing in the first constraint, so its coefficient in the first constraint, coefficient of s2 in the first constraint is 0, right? Similarly, we make the next row. I hope you understand. S2 is my second basic variable. Again, S2's coefficient in the objective function is 0. S2 is appearing in the second constraint. The right hand side of the second constraint is 3. And the coefficient of the variables, different variables in the second constraint are 1, 1. As you can see here, x1 is 1, x2 is 1. S1 is not appearing and hence 0. S2 is appearing with the coefficient of 1, that is 1. Right? This we do. Once we make this, next is we will be calculating the ZZ value. So next row will be of ZZ row. How to compute ZZ? It is computed like for any column, it will be 5 into 0 plus 3 into 0. Okay, so that gives you 0. For x1 column, it will be 2 into 0 plus 1 into 0. That gives you 0. For x2 column, yes, it will be 1 into 0 plus 1 into 0. That gives you 0. Similarly, for S1, it will be 1 into 0 plus 0 into 0, that gives you 0. For S2 column, 0 into 0 plus 1 into 0, that gives you 0. So what this value signify? Now the ZZ value in the solution column actually determines or gives the value of the objective function. See, here you have to understand one thing, that my non-basic variables are x1 and x2. Since they are my non-basic variables, their values are 0. We have assumed them to be 0. And the coefficient of s1 and s2, which are my basic variables to start with, they are 0 in the objective function. So finally, the value of z is 0, and that's what we get here. But are we satisfied with this value of z? Obviously not, because we are asked to maximize the value of z, but we are getting a value of z to be 0. So we are not happy with this. We have to go for a better solution. This is number one. And number two, we have to understand that whenever or whosoever your basic variables are, they are always going to form an identity matrix in the simplex table. So as you can see, S1 and S2 are my basic variables, and so they have formed an identity matrix under this S1, S2 column. Okay. Now once you calculate the value of ZZ, next you calculate the value of Cj minus Zz, and that Cj minus Zz is to be calculated only for the variables. It is not to be calculated for the solution value. Okay, so we write here and we calculate the Cj minus Zz values. My Cj values are 3200, and so you have to subtract the value of Zz from there to get the value of Cj minus Zz. So we get this. Next. So in the table we find that Z value is 0 with basic variables S1 and S2. We are not happy with the solution, so we have to identify who will be the entering variable to take up the basic variable positions. So for that, there is a rule for identification of entering variable. For maximization problem, the entering variable is 1 with the most positive coefficient in the Cj minus z0. And for minimization problem, the entering variable is 1 with the most negative coefficient in the Cj minus z0. So in our case, we can see the elements in the Cj minus z0 are 3, 2, 0, 0. The most positive being 3, x1 is entering. Once we identify x1 is entering, the question comes who will be leaving. And for that, we have to compute the minimum ratio. How to compute minimum ratio? The minimum ratio is computed by dividing the solution column element by the corresponding element of the entering variable column. So it is 5 by 2, that is 2.5, and 3 by 1, that is 3. So out of this, whichever is non-negative least, that will be the corresponding variable will be the leaving variable. So out of this 2, the minimum is 2.5, so the corresponding variable s1 will be my leaving variable. So x1 is entering and s1 is leaving. The element at the intersection of these two is called the key element. So in our case, the key element is 2. Once we identify that x1 is entering, so x1 will be replacing s1 in the new table, right? So in place of s1, we are going to write x1. Now next thing is how to make the new table from the previous one. So for that, we have to first get the elements of newly entered variable row by dividing the elements of the variable which it has replaced in the previous table by the key element. What is meant by that? x1 is entering and x1 has replaced s1 from the previous table, right? So my key element is 2. So to get the elements of x1 row in the new table, I have to divide all the elements of s1 row in the previous table by the key element, that is 2. Right? Once we get the elements of newly entered variable row, then we will determine how to get the elements of other rows. These are the steps of getting the elements of other rows. You can make a note of it and then we will see how to apply these steps in order to get the elements of other rows. So this was my first table. I am trying to make the second table based on my first table. Always remember that my first table is based on my standard form. My second table is based on my first table. My third table is based on my second table and so on. Okay. So let's make the second table based on my first table. So first I have to get the elements of x1 row because x1 is my newly entered variable. So that I get by dividing all the elements of s1 row by the key element 2 and hence I get the s. Next I have to get the elements of s2 row. In order to get the elements of s2 row, what I have to do is first I have to write the elements of s2 row from the previous table, that is 3, 1, 1, 0, 1. Now, in the key element column corresponding to s2 row, I have to identify what element is lying, that is the multiplier for the s2 row. So in the key element column, as you can see, corresponding to s2 row, 1 is there. One is there. This you can see, I think, right? So this one corresponding to s2 row, this one is the multiplier for the S2 row. Once we get the multiplier, we have to multiply all the elements of the newly entered variable row by this multiplier and subtract it from the elements of the previous table. Okay, so we have done it in the rough. The rough work is shown here, and then we get the elements of S2 row. Once you get the elements of S2 row, then we have to compute the value of ZZ as we have done in the last table, and finally we have to compute the value of Cj minus Zz. So this we get, and finally we get Cj minus Zz. So are we happy with this? Now I am getting the value of Z to be 15 by 2, right? That means my Z value has improved. It has improved from 0 to 15 by 2. Excuse me. But my maximum value of Z is 8, as we have seen in the graphical method, right? So I'm moving towards maximization, but I'm not happy with the value yet, as we can see that all my elements in the Cj minus Z0 are non-positive, are not, still one of the element is positive. That means there is further scope of improvement, right? So as we can see from the Cj minus Z0, there is a positive element half, corresponding to which x2 is the variable. That means x2 wants to come into my solution. Now if x2 wants to come into my solution, then one has to leave again. So we compute the minimum ratio. How to compute it? Solution value element by the corresponding value in the x2 or the entering variable column. So 5 by 2 divided by half, that gives you 5, and half divided by half, that gives you 1, right? So out of this 5 and 1, 1 is minimum, and hence S2 will be leaving and its position will be taken up by X2. The computation of S2 row elements have been done in the next slide. So this is what we have computed. This is how we computed. That has been shown over here. Next is, as we can see, there is a positive element in the Cj minus Z0, and since it's a case of maximization, there is a further scope of improvement, and hence x2 will be entering. If x2 is entering, so we have computed the minimum ratio 5 and 1, S2 will be leaving. So we are trying to make the third table based on the second table. Okay. So first we have to get the elements of newly entered variable row, that is x2. x2 has replaced x2, so all the elements of S2 is to be divided by the key element, that is half. This is the half, because entering variable is x2, leaving variable is S2, so this half is the key element. So we have to divide all these elements by half to get the elements of x2 row, which is the newly entered variable row, right? So we get these elements. Once we get these elements, next is we have to get the elements of x1 row. Now my key element is half, so corresponding in the key element column corresponding to x1 row, again there is a half. So half is the multiplier for the x1 row. Once we get the multiplier for x1 row, we have to multiply all these elements of the newly entered variable x2 with this half, and the resulting elements are to be subtracted from the elements of x1 row from the previous table, right? So what we get is this. The working has been done in the next slide. You can refer to this. After we do so, we have to get the value of ZZ, right? The same way what we have done for all these tables, and then we have to compute the value of Cj minus Za. As you can see, all the elements in the Cj minus Z0 are non-positive, which is an indication that optimal solution is reached. Since it's a case of maximization problem, when all the elements in the Cj minus Z0 are non-positive, optimal solution is reached, right? So my ZZ value is 8 and the corresponding values of my variables are x1 equals to 2 and x2 equals to 1, the same result what we have got in the graphical method. I hope you will appreciate that with each iteration actually I have jumped from one corner point to the other. So first my ZZ value was 0, I was not happy with that. Then in the next iteration, I got a ZZ value of 15 by 2, that is 7.5. But we were not happy with that also, since all the elements in the Cj minus Z0 were non-positive. One of the element was positive rather. And finally, we got a value of Zz equals to 8 and Cj minus Zz all are non-positive, indicating that the optimal solution is reached. So x1 equals to 2, x2 equals to 1 and the value of Zz is 8. So that is what we get here, and this is how we calculate or solve a problem, linear programming problem using Simplex technique. Thank you so much. If you have any questions, you can always put in the comment box. I will refer to those questions. And all the best. Bye-bye.